Let's start off today by just having a 10 or 15-minute conversation on area between curves. So as you were reading about this material and as you were watching the videos on how to determine the area between two curves, was there anything that came up that was unclear that you want to clear up as a class before we get into the groups and into the weeds today and working on some of these problems? So what about area between two curves did you find maybe less than clear?
When we were watching the second video, when it broke down, it made sense, but sometimes when it's more than two curves, like they had the third one added in, we were trying to split it up. Sometimes I was getting confused on which one should be on the top and which one should be on the bottom.
Ah, okay. Right. So if it's just the area between two curves, usually it's fairly straightforward. If you know which curve is on the top and which curve is on the bottom, then what do you do? So if this is, just if I label this graph here, if this curve is y equals f of x on top, and this curve on the bottom is y equals g of x, then how would I set up an integral to determine the area between these two curves? Let me try and shade this in. From x equals 1, let's say, to x equals 4. So if I wanted to determine that area, then what integral can I set up that determines the area between those two curves?
Integral from 1 to 4, f of x minus g of x.
F of x minus g of x. Integral taken with respect to x. Okay, so tell me, what's going on when we're taking a subtraction? Why are we subtracting f of x minus g of x? What are we really doing there? What's the purpose of that subtraction?
Clear out all the stuff under g of x.
Okay. Yeah, that's one way to think of it, right? Because if we just have the integral, so kind of what you're getting at here, is if we just look at the integral of f of x, what are we really getting?
Everything below.
Below f of x and above what? The x-axis, right. If you just take the integral of a single function, you're getting the area underneath its graph and above the x-axis, right? Or if you like, the area between the graph and the x-axis, where that area is signed to be positive if the function is above and negative if the function is below. So if I just integrate f of x, I'm going to get this area in here. And if I just integrate g of x, I'm going to get the area between g of x and the x-axis. So what's happening when I'm subtracting these two? I think you said it already. Let's say it one more time to make sure we've got the idea here.
Trying to get rid of this g of x. I don't know. I got lost.
Okay. So there's a couple different ways to think of it. First, let me give you this idea. Thinking of this as f of x, the area under f of x minus the area under g of x, is saying, well, let's take this orange area here to begin with, and I'm going to subtract the green area, except the integral of g of x in this example, is it positive or is it negative? It's negative because g of x is underneath the x-axis. So if I'm subtracting that negative area from the area in orange, what am I really doing? I'm really adding. Exactly. So in a sense, what I'm doing when I'm doing this particular subtraction of two integrals is I'm taking this area and adding it to that area, which is exactly what we want, because it just so happens that the green area here is negative. So that's one way to think about what we're doing here. But the second way to think about it is a way that I think we're going to hang on to for a little bit longer. Rather than thinking of this as two separate integrals, we're going to think of it as a single integral in the following sense. So let's remove the distinction between orange and green here. And instead, let's do this. So again, here's x equals 1 on that side, x equals 4 on this side. And what I'm going to do is mark a location on the x-axis. So in a sense, I'm just going to pick a value for x that's arbitrary. So here's where I'm going to think of my x as being, somewhere between 1 and 4. And I'm going to ask the question, what is it exactly that I'm trying to measure? What is it exactly that I'm trying to add up with an integral? And what I'm trying to add up with an integral is the area of some little slice of this region. So I'm going to kind of draw it like, draw it like this. So I've got a little rectangle sitting here at the location marked by x, and x is going to range from 1 to 4 to sweep out the entire area that I have here under the graph, right, between the graphs. And so this little rectangle here has a certain amount of area to it, and how much area it has depends on where my slice is taking place. And whatever that area is, I'm going to call it, well, I'm not going to call it A, because I want to think of this slice as being really, really thin, so thin, in fact, that this quantity, this area, is going to be virtually indistinguishable from 0. And because it's such a small quantity, instead of calling it A, I'm going to call it dA. So some little tiny amount of A, call this an infinitesimal element of area. Area element. This is a trope that we're going to use more than once, both today and in tomorrow's class on solids of revolution. So that's where we're going to start with this. We're going to say, let's pretend that that's a little rectangle sitting there, and the area of that rectangle is dA. Well, how do you find the area of a rectangle? Any old rectangle. Yeah, width times length, width times height, whatever it is that we call those two dimensions. Because we're looking at this straight on, let's call it width and height. So to find the area of this teeny tiny little rectangle, I should just multiply its width by its height. And its width, because its width is some teeny tiny little piece of the x-axis. In other words, if I'm measuring this up, I'm going to measure it as the distance in between those two places on the x-axis. And I'm going to call that width dx, some teeny tiny infinitesimal little element of length along the x-axis. Infinitesimal length element. So that becomes the width of my teeny tiny little rectangle. And so far, this is all just sort of definitions, right? There's not much action here yet. Where the action comes in is when I insist on measuring the height of this rectangle. And when I measure the height of this rectangle, now I have to ask the question, well, what is the height of this thing? Well, how can I measure the height, which is, by the way, a vertical measurement on this graph, from this point on the top, which is on the top graph, to this point on the bottom, which is on the bottom graph? Well, we could call it dy. If I call it dy, I would think of it as being some teeny tiny little distance on the y-axis. But I'm actually going to, this length is something bigger than dy. This length has something to do, not just with y, but with the heights of these two functions, f of x and g of x. Right? So suppose for the moment that this top graph is y equals, actually what does the app say it is? X squared over 5. And the bottom graph is y equals minus the square root of x. And let's pretend for a moment that I'm at x equals 2. So we're just going to pick a specific value for x. Sometimes this is a good way to get started. So if I pick the value x equals 2, then what is the y-coordinate of this point on the top of that line segment? 4/5, because why? Where'd you get that? Exactly. The y-coordinate of that point, because the point is on the graph of the function f, the y-coordinate is just f applied to the x value. So f of 2, which is 2 squared over 5. Likewise, the coordinate of the point that's at the bottom of that line segment, y equals, because the bottom portion is on the graph of g, y equals minus square root of 2. And now to measure the distance, the height, in between those two, what am I doing? If I want to know how much vertical distance there is between 4/5 and negative the square root of 2, what operation am I going to do to those two numbers?
Minus.
Exactly. Subtraction.
But what is going to be adding?
Really, from an absolute value standpoint, it's going to be adding, right? Because the g happens to be negative and f happens to be positive. But the great thing about this is we don't even need to have that in mind, that this is going to work regardless of whether or not we have both graphs above the axis, both graphs below the axis, or one on the top and one on the bottom. Okay. So to generalize that, instead of subtracting those two specific values, we'll just subtract the two general values. Y equals f of x is the y-coordinate of the point on the top of this line segment. Y equals g of x is the y-coordinate of the point on the bottom of this line segment. And so the height of that rectangle drawn at x is exactly the difference between f of x and g of x. So that's why this whole method works. And I like to call this the method of slices. It's where we have some big area in this example that we want to determine. And to figure out what that area is, we're going to cut it up into a bunch of little infinitesimal slices and figure out what is the area of each one of those little slices. And because each slice is easy, it's a rectangle, and we know how to find the areas of rectangles, width times height, then all we have to do is compute the area of this infinitesimal rectangle, which is an infinitesimal quantity because of this dx sitting out here. And then add up the areas of all those infinitesimal little rectangles over the range that we're interested in. So in our example, dA is going to equal f of x, which in our example is x squared over 5, minus g of x, which is minus the square root of x, dx. And there's where the minus a minus turns into a plus. And then to find the total amount of area, I'm just going to add up the dAs. In other words, I'm going to take the integral from 1 to 4 of x squared over 5 plus the square root of x dx. And here's a true statement. For all of these problems that involve integrals that are useful for something, setup is everything. That if you make it to this stage in the problem, you're 85 or 90% of the way home. The setup is everything. I mean, obviously, because this is a calculus class, I want you to evaluate the integral when you're asked to evaluate it in an accurate way. Apply the fundamental theorem of calculus, find an antiderivative, subtract your limits, etc. But really, where most of the slips are made in problems like this is in the setup, is in the process we just did. And in the calculus that follows, generally by now you're pretty well practiced at doing that phase of it. So if you're going to make a mistake, usually it has happened by now. So let's finish this example and then get you into your groups. So how do I find an antiderivative for x squared plus, x squared over 5? Let's start with that one. Okay, so increase the exponent by 1 and divide by the new exponent, which is going to turn what used to be 5 into 3 times 5. How about the square root of x? Exactly, because first, before we do the antiderivative, we rewrite that as the power x to the 1/2. And then we know what to do because it's a power. Increase the exponent by 1, make it x to the 3/2, and then divide it by 3/2, which is the same as multiplying it by 2/3. So there's our antiderivative. And then to finish, all we have to do is evaluate that antiderivative. at 4 and at 1, and subtract the results. Anyone know what 4 cubed is off the top of their head? 64, great. 64 over 15. Plus, what's 4 to the 3 halves, by the way? Close. 4 to the 3 halves is the same thing as square root of 4 raised to what power? Right. So that's 2 cubed, which is 8. So here I'm going to have 2 times 8 over 3, 16 thirds. So that's the evaluation at x equals 4. And then the evaluation at x equals 1, which we'll subtract from over here, is going to be 1/15 plus 2 thirds. And so in the end, we get 63 over 15. Messy fractions abound. 63 over 15 plus 14 over 3. And if you like common denominators, we can make this multiply by 5. We get 70 plus 63, 133 over 15. And that, I believe, is lowest terms. So again, the calculus is probably all familiar, but the new thing that we're going to hang on to is how we set up that integral. By taking the whole volume that we cared about and picking on a slice, picking a value for x and saying, well, what does it look like if we slice the area that we're trying to compute at that point? And what is the area of that slice? And once we know what the area of that slice is, we can just add up the areas of those slices. And that's what the integral is there for. Questions on this example? Yeah?
Yeah, do we have to go that far? Do we definite or the definite? We just leave it as like, you just substitute a 4 and substitute a 1 and just leave it subtracting.
I guess that depends on how much time you have to work on the problem, and or just how hairy the arithmetic is at the end. I mean, clearly this is not an arithmetic class, so I'm not going to be hawking your fractions as much as I might in another class. But that being said, you know, for your own sake, take it as far as you're comfortable taking it. If you have a calculator and you want a calculator to help you with that arithmetic, I'm totally cool with that. So calculators are good on quizzes, tests, you know, homework, anything we do. I'm not going to make you put your calculators away for that. So use them as a tool. That's what they're good for. Other questions on this example before group stuff today?